Hello, my name is Robert Smith, and I'm with New River Community College's Academic Assistants, and today we're going to do a little more work on Lewis dot structures. So we're asked to write the Lewis dot structure for the following molecules. And the first one we have is ammonia, NH3. And again, you're going to have to refer to your periodic table of elements at any given moment to make sure that everything is making sense to you in terms of what I'm discussing in this next couple of minutes. But we're going to start by counting the number of valence electrons. So nitrogen is in group 5. It's going to have 5 valence electrons. And then we're going to have 3 hydrogens. So 3 times 1 is 3. So that's going to be an 8 for our total number of electrons that we have to account for. And that's most of what Lewis dot structures are going to be involved with, is accounting for the valence electrons. You don't lose any, you don't gain any, it's just accounting. So we're going to start with our basic setup for the molecule. Now, nitrogen is our more electronegative species, so we're going to put that as our central. Hydrogen is not really going to be a central atom, so we're going to do a hydrogen over here, and a hydrogen over here, and a hydrogen up here. Why not? Okay, so we've got 3 hydrogens and a nitrogen, which is exactly what our chemical formula states, and we have a total of 8 electrons to deal with. We know hydrogen has 1 electron apiece, and that it's going to bond with nitrogen. So we've got that's 2 electrons, 4 electrons, 6 electrons. But now we have 2 extra electrons, and they're not going to get bonded to hydrogen because hydrogen now has the 2 electrons that it wants to fill in order to be more like helium in its own way. Hydrogen is very happy with 2 electrons. Nitrogen still wants 8 total. And right now it only has 6, 2 from each of the bonds. So it needs that other 2. So the last 2 just get tacked on there. Those are called lone pairs. And that's the Lewis dot structure, a very basic Lewis dot structure for ammonia. For our next molecule, we have formic acid, and we'll start with carbon. Carbon has 4 valence electrons, plus 1 valence electron for each hydrogen, and there's 2 of them. Okay. Plus oxygen, which has 6 valence electrons, and again, there are 2 oxygens. So that total is going to be 18 valence electrons, because 4 plus 2 is 6, plus 12 is 18. So in drawing this out, it takes a little bit of playing around. And it usually involves things like formal charges. And we'll be discussing formal charges in our next video. But let me just show you the basic for this. So we're going to assume that carbon is going to be our central atom. And oxygen and hydrogen are not. So we can do a number of different things. We could make it so that, in a brief preview of formal charges, we could make it so that carbon is simply singly bonded to 2 oxygens and 2 hydrogens. But that would be incorrect. And the reason we know that's incorrect is because the formal charge on the oxygens would be different, because this one would have potentially 6, and this one could have as little as 4. And the resultant would be that you'd have one oxygen that is of a +1 formal charge and the other one at a -1 formal charge, which is not preferable to our alternative structure, which is the correct structure. Correct structure is going to have carbon over here, and you're going to have a hydrogen, an oxygen, and then a hydrogen. There's going to be a hydrogen attached to one of the oxygens. So now, if you were to do the formal charges for this particular setup, you would end up finding, after it's all said and done, that both of your oxygens have a formal charge of 0, which makes it the optimal structure for this particular molecule. So now we got to take care of our 18 electrons, now that we've decided on the shape. So we've got a single bond with the hydrogen and its nearest species. So that's 4 out of the 18, so we have 14 left. Let's go ahead and make a single bond to the oxygens. That doesn't take care of everything quite yet, but let's just go ahead and look at it like this. So that's 8 total. We have 10 electrons left. Generally speaking, central atoms are going to be happier if they can make a double or a triple bond with something rather than a single bond, rather than having a lone pair on it. On our previous example of ammonia, you weren't able to do that because hydrogen is very happy. It doesn't want more than 2 electrons. But oxygen can take more than 2 electrons. So let's just go ahead and make a double bond here, because oxygen already has 2 bonds with hydrogen, one with the hydrogen, one with the carbon on our other oxygen. And this oxygen up at the top has now 2 bonds to it as well. So let's do a little quick counting. We've got 2, 4, 6, 8, 10 total electrons in use, and we need 18 total. So carbon has its complete octet, hydrogens are happy, so now we just need to add a couple of electrons onto both of the oxygens. So we just need a couple of lone pairs. This does take some practice. I'm not expecting you to, fully grasp it just looking at it, but that's really what this whole thing is. It's just to kind of give you a basis, but do is take some time and practice these. Choose some random molecules. Don't get too crazy. Don't choose something that's, obscene and has, more than elements than you care to deal with. But 4 elements, 6 elements, something in that range can be challenging. Generally on an exam, they probably won't give you anything that strenuous, but you just want to be able to be comfortable with creating your arrangements and assigning your electrons. So let's look at our last one. It's just a phosphate ion. It's relatively simple. Looking at a phosphate ion, you've got your phosphorus in the center, and then it just has 4 bonds to its respective oxygens. But this is deceptive. And chances are in this class you may not deal with anything in your 3rd period, because 2nd period has to maintain its octet. It cannot break the octet. 3rd period nonmetals can exceed the octet. It can have what's called an expanded octet. And when that happens, you can have an interesting scenario, and this is one of them. So let's look at phosphorus and let's look at oxygen and our extra 3 electrons. So we've got 5 valence electrons plus 4 times 6 plus 3 So that's going to give us a total of 32 electrons to deal with. Now, if we were to have these singly bonded and we were to assign the lone pairs, it would seem like we're done because you've got 6, 8, 12. It would seem like we're done because you would have 6, 12, 18, 24 plus 2, 4, 6, 8. So that's 32. You have the total number of electrons you need. You have the total number of bonds that would make this a happy ion. Of course, this has a -3 charge on it because it's a polyatomic anion. But really what's going to happen is you want to have a, you want to look at this in terms of that it's a PO4 with 3 extra electrons just tacked onto it. And because of that, what actually happens is experimentally we can show that what really happens is the phosphorus double bonds with one of the oxygens, and it's the same number of electrons, but it's a more stable molecule. It's a more stable anion, and we know this by writing out the formal charges, because otherwise all of the oxygens have a -1 formal charge, whereas if you even had one of them that was double bonded, that's at least one oxygen that has a formal charge of 0. And again, we're going to discuss formal charges in the next video. But the ultimate result is that just that extra little bit of bonding that occurs, that violation of the octet, results in this being a more stable polyatomic anion.